I can't speak to that. But we left off last time doing this exercise to illustrate dynamic data structures in Java, lists and sets. In the interim here, what I did is I went ahead and generated my own data. I couldn't find anybody from 155A. So I had no idea how much data they actually had. So I just generated a whole bunch of data of 5-digit zip codes, including ones that begin with 0 here. And guess how much I generated? A million of them. Right? Now, of course, I wrote a program to do that. But let's go ahead and revisit that solution again. But I don't want to do it on a million. I want to do on, say, the first 100 of them. Well, remember that you've got a lot of these really cool functions and methods that you can call to use on a list. And one of them is going to be, let me see, am I over here yet? There we go. All right, dot sublist. If you only want a sublist from 0 to 100, right, or 0 to 99, right, it will give you a sublist. So that we're only dealing with 100 zip codes. That allows us to check to see, well, just on this small piece of data here, I could go down to 10. Is my code correct? Right? So let's go back over, let's review without going back what we could do with this thing. So first of all, what we could do is and note here that I've also treated them as strings, right? This is just loading it up from this file. Then we're only taking the first 100 of them and we're treating them as strings because some of them begin with a 0, right? So because they begin with a 0, they're going to be strings, right? So we had a unique zip codes, right, is equal to just a new hash set. And then I give it zip codes as the argument here. Normally, if you just want a regular old empty hash set, it's empty. Otherwise, if you want to take that list and dump it to a set, it'll get rid of all the duplicates. Yeah?
Is sublist inclusive or exclusive?
Good question. It's inclusive on the first one, exclusive on the second one. So that you always know that it's B minus A size, 100 minus 0, you're going to get 100 of them. If you wanted to start at 10, now you're getting 90 of them. Right? So there you go. System.out.println, or unique codes. There we go. And let me show you that we're only getting a subset of them, right? So there's definitely not 100 there, right? Zip codes. That looks way more than 100 though. Oh, they're probably all 100 unique because it's all random, right? And 5 digits means that there are 10,000 unique ones, so I am probably actually getting the number of unique ones. Let's ask the size though, right? There might be like a duplicate in there somewhere. Probably not though. But if I expand this out to the entire list, 1 million zip codes with only 10,000 possibilities, 10,000, right? 100,000 possibilities. Then of course I'm not going to have a million. I'm going to have 999,993. Am I off? 100,000 possibilities, right? 99999, right? Yeah. Okay, so that's a good indication that we're missing 7. So there were 7 unique zip codes that never appeared in my random data. Right? Good? All right, that's not what I want to look at though. What I want to do is, given the unique zip codes, I want to iterate through all 1 million of them, and I want to count up the number of times they appear. So for each zip code, which is a string, for each string called code in unique codes, I will iterate through the zip codes up here. So for string, I can't use code again, can I? In zip codes. I've got code. What should I do? Code the first, code the second. Again, naming things is difficult. So I'll go ahead and go with unique code. Actually, a zip code. There we go. That's why arrays, lists, sets, you pluralize them. Right? Single things, zip code, you do not pluralize. So that you can say for each zip code in zip codes, then we've got this. Right? So for each code, if the code is equal to zip code, then I will say counter plus plus. Right? And that means I need to create a counter, initialize it to 0, and then print it out after I've looked over everything. So system.out.println, or at printf, let's say, %s zip code appears how many times, %d, and the line, and that's going to be zip code and count. Right? So again, to walk through this, for each unique zip code, I'm going to set a counter, and then for all the zip codes in the zip code data, if we've got one that matches, then I'll increment a counter, and then we output this. Right. So let's try it. Everything only appears once. Well, that makes sense because we're only doing 100 things. I had hoped that it would come up here, but this is not failing like I wanted it to. Is this how you, in either language, is this how you compare a string to a string? Nope. This is for numbers. When we get to strings, we'll look at how to compare them, but generally we'll go with dot equals. So if that code equals the zip code that we're currently counting, then I'll increment the counter. And we're going to get the same result here, a bunch of ones. Okay. Let's expand this out to the entire list. All right. Okay. So other than printing this stuff, let me tell you that it's going to be very, very inefficient. It did not start at 7.7 or 7.6 whatever. It's not going in order, is it? Looks like it is going in order. Why is it going in order? That's just a quirk. I have no idea why it's going in order. It seems to be going in order. But it shouldn't be. We saw that it wasn't sorted, right? With just adding 3 things, 10, 20, and 30, it was 20, 10, and 30. So there we go. It's not going in order. Now it's down to 5s, right? So you know what? I/O is very expensive. Input and output is very expensive. Let me go ahead and forego that for now. Right? Input, output is the most expensive thing that you can do. Let me go ahead and just run the program and see if I could get an answer without printing it out. Is 1 million things big data? No. Well, let's think about this while this is running in the background, because this is a preview of something we're going to do later on, right? How many unique zip codes are there? If I've generated every single zip code, 99,993 was the exact count, right? So let's just say 100,000. Right? How many zip code data points did I generate? 1 million. Right? So for each one of those 10,000 zip codes, go through 1 million pieces of data to count up those unique things. In my mind, that's going to be what? I can't do that in my head. So let's ask Wolfram Alpha. 100,000 times 1 million. We call them 1 to the 11th, 100 billion. 100 billion pieces of data. It's still processing. 100 billion operations. Now that doesn't sound like a lot, but it is, even on a modern computer here. Right? We'll just go ahead and let that run in the background here for a little bit. While we do that, let's think of a better way of doing this. Okay? So, lists, sets, whatever. What was I trying to print out? In fact, let me undo that. What was I trying to print out here? I was trying to print out a list of zip codes to the number of times that they appear. I was trying to output basically a mapping from a zip code to a count. Right? For example, and let's just say, I don't know, 68508, which is UNL's, one of UNL's zip codes. And it appears, I don't know, 12 times. Right? So this idea here is what a map is. Right? What I'm trying to map is a string to a integer. Right? Now some of those are going to be 0, some of those are not going to appear, some of them are going to be 12, some of them are going to be 42. Right? That's the data structure that I'm going to use to solve this problem, while that other approach is still running. So I'm going to create a map that maps a string, comma, to an integer. The same Langle-Wrangle syntax here is a parameterization. It's a key. Maps are key to value data structures. think about a regular old array. An array is a kind of a map. An array maps integers from 0 up to n minus 1 to values. In other words, the keys are restricted to integers, and they're restricted only from 0 up to, if there are 10 elements then it's 0 up to 9. And you can't miss any in between. In other words, an array is nothing more than a map without any of the great features, right? Without any flexibility to define a key however you want. Our key here is going to be a string. So if I've got a string here, 68508, I can map that to the integer value 12. Let me show you how it works before we actually solve this problem. By the way, it's still running. Right. I'll just call it m for now, is equal to new hash map. There we go. I can put stuff in there. M dot put. Right? It's not add because it's not a list, it's not a set. It needs two things. It needs the key and the value. So I'm going to go ahead and say Chris maps to, I don't know, 127. Right? What's the significance of that?
Nothing.
Okay. Isn't that a...
It's our graduation.
Oh, okay. No, I was thinking Suzuki's number, but then Suzuki took it from Angels guy. Was the best baseball player. Now Otani is the best baseball player. All right, nobody knows baseball. Never mind. Anyway, m dot put. Let's go ahead and put Jackie. We'll map him to 42. Now do you know what I'm talking about? All right, Jackie Robinson. All right, so you can put whatever you want in there, right? You can reassign values. So I'll go ahead and change the key. I'll change what I am mapping to. Now I'll go ahead and map to 24. There we go. Right. Or m dot put. You can remap. You can remap something entirely or something like that. You can retrieve values, right, using the key. Right? So I could say m dot get, and now here you only need the key. So Chris. And that will return an integer value, x. And you'll see now that it's 24 if I system.out.println x. Right? Let me go ahead and run this. I don't know if that'll affect the other one or not, but that's okay. Proceed with this launch. Oh, sorry. Hash map, got to import that. Yeah, go ahead.
What would happen if you changed the key instead of the map or the value?
Then it would just map a new key. The old key would still be in there. The old key value pairing mapping would still be in there. Right. There we go. Let's run this now to see if it works. And it does. 24 there. I think the other one is still running in the background. Let's find out. Yep, it is. Okay. All right. You can change values. You can reassign values. You can put values in there. You can check to see if there are values in there. For example, m.get or has key. No, where is it? Dot contains key. There we go. Contains key, Chris. Oh, yeah, you know what? Let's keep it like that. System.out.println contains it. Now this is really slowing my computer down, so I might have to actually kill that other program. Otherwise, nope. So does it actually contain CHRS with a capital H? Mashed keyboard there? No. So it's case sensitive. Yep, nope. At this point I am going to kill that. I was going to illustrate that it's actually going to take days, weeks, months to do this. I don't know. Let's go ahead and kill it. The final solution that we're going to give you here with using this data structure called a map is going to be done in a second. I guarantee you. Right? All right, so does it contain the correct spelling of my name? Yes. Contains it. There is a little bit of a lag here because we're still loading up all this data. Let's go ahead and get rid of that for a second, and it'll be much faster. All right, so you can ask whether or not it contains a key. You can try doing something like this. Integer, or actually, no, int x is equal to m dot get. I don't know, Cody. There we go. Actually, who should we be signing? Pete Alonso. And I've already got X, so let's go with Y. System.out.println Y. There we go. Uh-oh. Does it contain Pete? The key Pete? No, I never put that in. So what happens when you ask for something that doesn't exist? What value do you get back? Null. It will work without an exception here if I change this to big I integers, which can be null. Right, there we go. It just tells you that it's null when it prints it out. So if you go asking for something that doesn't exist and you can ask this question, well, does it contain the key? And if not, then don't do it. Otherwise, you can just go ahead and get it, understanding that it'll be null if it's not there. Right? So you can put stuff in, you can take stuff out, you can remove stuff, you can clear it out like remove key. Yeah, remove the key. You can remove the key value pairing. You can replace it, etc., etc. We call this CRUD. The 4 basic operations on any data are create, retrieve, update, and destroy. Right? So you put stuff, create, you can put stuff in, retrieve, you can take stuff out, update, you can replace stuff, and destroy, you can go ahead and remove stuff. Right? And that's usually in the context of databases, but it's the same idea. Right? There is the basic usage of a map. I'm going to go ahead and put this in the notes so that you have it. There we go. But otherwise, let's go back to this illustration of how to use this at hand here. So let's go ahead and actually load this data again. Any ideas? Instead of doing, what was it, 100 billion operations, right? What could I do? I could go through this data, and with the map, what I could do is I say, okay, well now I've got a key. I've reached 89858. I could ask the map, have I seen this before? And if I've seen this before, how many times have I seen this before? Because remember the mapping. It's from a string, the zip code, to the number of times it appears. And if it says that it's appeared 5 times before, well, great. Now, how many times have I seen it? 6. Increment that and put it back in the map. Next time you see it, increment it again. Now I've seen it 7 times. Now I've seen it 8 times. What about ones that don't appear? They'll never end up in the map. Right? So that's my map. That's how I'm going to use my map. Right? Let's outline that. Right? Again, when you're writing algorithms, you whiteboard it. Right? So for each element in zip codes, right, get the value from the map M, right? If this is the first time, initialize it to 0. We'll understand that in a second here. Otherwise, else, this is the second or the third or the fourth or the 5th time that we've seen it, or some other time. Else, increment the counter and put it back in the map. All right. Now I wrote this as an if-else statement, but just to get the ball rolling, to get the idea. Right? So we could initialize this to 0, and then subsequently, if we ever 1, and then every time we see it afterwards, we could increment it. But what I'm going to do is I'm going to make the code even simpler. Regardless of the number of times that we've seen it 1 more time. So I'm just going to increment it no matter what. In other words, no else. So if this is the first time that we've seen it, initialize it to 0, because the very next line, we're going to increment it to 1 the first time we've seen it. Okay? There's my outline. Now let's go back and translate each one of these lines into actual Java code. So for each element in zip codes, we already know how to do that. For each string called zip code, in the collection zip codes. Now again, why am I doing it that way? Because I don't really care about the index value. Right? I can use an enhanced for loop here to iterate overall 1 million elements. Okay? I'm not doing 100 billion. This is 1 million. Right? Way, way smaller. Now, get the value from the map M. So, int, I'll just say count is equal to m.get zip code. Now remember from our demonstration here, is that safe? What if we've never seen it before? This is the first time we've seen it. If this is the first time we've seen it, we need to initialize it to 0. This could be null. So let me go ahead and put it into a variable that can be null, big I integer null. Okay? I've got the count. How do I determine if this is the first time we've seen it, or if it's the second or the third or the fourth or whatever? Under what condition will it be the first time? If count is null. If count is null. That's C. How do we do null in Java? All lowercase, as the magenta color indicates there. Right? So if this is the first time that we've seen it, I'll initialize it to 0. Right? Then I'll increment the counter, count, plus plus, right? And put it back in the map. M dot put zip code to count. Right? It's very, very simple. Much, much simpler code than 2 nested for loops that do 100 billion operations. Now I'm doing 1 million operations. Yeah,
When would you use m.put as opposed to m.replace?
you could replace.
Is
That-
there just like
Yeah.
reasons would you do there? Or is it
No, no. It'll just m dot. It's a good question. I don't know. Replace does a what?
What?
Except that it does some safety checks up front. So there it is. All you have to do is look at it like, why'd you do it that way? Because I wanted to. All it's doing is some basic checks here before it calls that function, and it's all it's doing is a put value, and that put value is abstract. It's probably is it abstract? Yeah, it looks like it. Why is it not labeled as abstract? It's not native, is it? Anyway, now we're getting into low-level Java stuff. Anyway, put. There we go. All right. Now, remember that it was still running, and I'm telling you that it's going to take days, if not weeks, to do it the other way. 1, 2, oh. And half that time was just loading the data from the file, and it was done immediately. Now, if you want to actually go through and print the stuff, that leads us to another question of maps. Like sets, they're unordered. I can't just say for the first element, for the second element, for the third element, because it doesn't work that way, right? We've got values and we've got keys. So we need to iterate over those. I'm going to show you the simplest way to do it. For each key, right? So for each key, dot, 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 for string zip code, in the collection zip codes. Let me try that, or actually what was my map called? M, there we go. Let me try that first. That's not gonna work because it's not like a set, it's not like a list that just has things in it. It has pairs of things in it, a key and a value. Now there is a way to do that, but this is much easier. If you just get the key set, right, that's a regular old set, right? And you can go ahead and print for each one, the value count, int count will be zip m.get zip code. Now I've got the key and I've got the value, and I've got sensible variable names for them. So now I can go with my system.out.printlf and print f zip code %s maps to %d and the line, and this is going to be zip code and count. There. Now that will probably take a little while because of course printing is quite expensive, but not that expensive. There we go. It's still not satisfying. Right? It was all over the place, wasn't it? Right? Now I'm getting those values. How can I know those values are correct, first of all? 61280 appears 12 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Back to where I started. Looks like it works to me.
Yeah.
Right? So this same basic operation is in any text editor that you do. Right? Now we know how it can be done, right, in code. It's still not satisfying though because it's not in order. It's not in order because maps aren't in order. It's not in order because sets are not in order. So what could we do to make it so that we would print out these keys in order? I would first have to dump it to a list of strings. and this is ordered zip codes, is equal to new array list, there we go. And I will put in the m.keyset. Right. So we've already seen how we can take a list and dump it to a set. Now we're taking a set and dumping it back to a list because we want to sort it. Collections.sort. Ordered zip codes. There we go. Now I don't iterate over the key set. Instead, I iterate over ordered zip codes. Let's run it again. It's not going to add too much to it. There.
But isn't that sorting the strings?
It's sorting the, what, did you want to sort the values?
Oh, I guess it doesn't have. Oh.
If you want to do that, we could do, I'm going to leave it because that's what I wanted to do, but let's go ahead and sort the values. What is the most common and least common zip code in our data set? More precisely, how many times does it appear? So a list of integers counts is equal to new array list of m dot, not the key set, but the values. So you can get all the keys, you can get all the values, you can do whatever you want with them. Right? They're both sets. Or no, that's going to be a list, isn't it? It's just a collection. It's neither nor. You don't know what you're getting. So I'm going to dump it to a list, and then let's print it out. Well, actually, let's sort it. Collections.sort. Counts. Why? Because where's the answer to my question? What's the most common? What's the least common zip code? The counts, that is. If I sort it in increasing order, where would the maximum value be? At the bottom. Where would the minimum value be? Up here at the top. Right? Now, obviously, there's zip codes that don't appear, and it won't be 0 here. But counts.get. What's the first one? 0. Right? So int min count is equal to that. Int max count is equal to counts.get the one at the last one, which would be counts.size minus 1 because it is 0 indexed. System.out.println min max is equal to %d %d. And the line min count max count. Print f. Save. So it's just a different question. And after this is done printing, there we go. So there is one zip code in there, at least one zip code that is unique. It only appears once. There's a zip code in there that appears 26 times. What are they? Can you go backwards? Can you start with a key, a value of 26 and go back to where it came from that gave you that value? Not with this, right? We call it, a mapping is basically a function, right? X maps to Y, right? Can you invert it? Only if it's, do you remember this term, bijection? Right? Surjection, bijection, injection. Okay, you'll learn that in 235, or you'll relearn it in 235 if you've forgotten it. Onto or one-to-one? Ringing a bell? Maybe, maybe not. Okay. Yeah. Oh, you're already in linear algebra. Okay. So this is just basic functions and mapping. Can you map that? No, because it's not a bijection. It is a one-way. What if there are 4 zip codes over here that all have a count of 26? Which one do you map back to? Right? There are 4 zip codes that map to 26. There's that one unique value, but well, which one do you go to? Because then it ain't a function, right? Just like a circle is not a function. Why? 1x maps to 2 things. Right? That's not a function. That's called a relation, right? But that's different. So what we have to do is we have to go back and do some manual digging, right? So for each string zip code in the collection, m.keyset, let's go ahead and get that count. Int count is equal, I could probably just copy and paste it from up there, but m.get zip code, right, there we go. If count is equal to 1, then that's a minimum value, right? So let's print all the minimum count zip codes. If that count is 1, which we now know is 1, right? Then, actually I don't even need to hard code that. What if the data changes? Let's make it a little bit more robust there, right? System.out.println zip code. If I want to do it for Max. Why are you not magenta? There we go. All right. Max zip code. It's going to be, we need to distinguish these now that I'm printing out two things. Min zip code is going to be this. There. I have no idea what the actual assignment is over that prompted this and that inspired this, but what is wrong up there? All right, it's gotten confused. Let's open it back up. Oh wow, do I have a missing thing somewhere? Why are you getting confused? Let's run it. I'd probably have to restart it. It got confused or something about there being an actual problem. But now you see there's a bunch of min zip codes that only appear once. What's the max? There's one. Do we have any other max? Here, expand this out. Oh, there's another max. So, no, it is not unique. Right? And I wouldn't expect that with a randomly generated data like this. But you can ask a whole bunch of questions, and all of your questions like this, these statistician questions become super, super simple if you're using a proper data structure like a map. Not only that, but they become super, super efficient. Instead of 100 billion operations, you're essentially only doing 1 million. Right? And that's what? 1,000 times fast, 10,000 times faster. At least for this particular one. Yeah.
So for the maps, how does the map know like which value to do for just like a random like zip code?
It's under the hood. There's something called a hash table, and at the end of the day, there is an array somewhere. Right? That's the ugly truth is that's all we really do have is arrays. All right, and so what happens is there's this hash function that, given this key value, maps to a particular index. Right? So you don't have to go through and find the index that it contains. Instead, there's this magic function. It's not a magic function. It's just a hash function that says that element is located at index 5. You jump to index 5, and there's your count. Right? That's why it's so efficient. It just jumps to these random access locations. How it does it? It's that hash function. Right? So there's this hash function that takes your input, your string, and then does something with it. In fact, we can look at what it looks like. Find hash code. There it is. There it is. Right? That's hash code. So it's doing, if it's Latin, then it does one hash code. If it's Unicode, it does a different hash code. Let's see what that looks like. And so it's all this mathematical magic. Right? That's what it's doing. You can always look how you can always look at the Java source code and see how the sausage is made if you really want.
Does the visualizer show how that works?
No. But you can do something like this. You could say at the very end here, string s is equal to 68508. There we go. There's our zip code. What is its hash code according to Java? Int x. It's just an integer. S dot hash code. You can call that function, and you can println x. Eventually, you'll get to. Now we're gonna have to rerun everything again, but that's okay. It doesn't take that long. There's its hash code. Right? Now it winnows that down to whatever size array you have. You're not going to have an array of size 51 million and change. Right? But then you get into things called collisions, collision resolution, perfect hash functions, and it's all data structures and algorithms at that point. For now, though, I just want to use it because I want to solve problems. I want to, for whatever reason, I want to know about this zip code data. Right? All right, so I'll make sure that you have all that in the notes. But believe me, once you start using and seeing, once you start using a map, you'll start seeing every piece of data as a map. And once you've done that, you'll never go back to a regular old list, a regular old set, or certainly not regular old arrays. Dynamic data structures are so much better. And then you'll start wondering, why doesn't C have this stuff? And well, it's because it's a bare bones language. If you want that stuff, you can have that stuff. You just need to either write it or bring in a library to do it. Okay? All right, any questions? Otherwise, that was a good divergence. But let's go back to pitfalls with arrays in C. Right? In C, you are, let me emphasize that, you are responsible for memory management. Right? You have to keep track of the size of arrays that you create. You have to clean up after yourself when you no longer need the memory, right? And you have to be responsible with the memory. You can't just go, what did Bret Hart say? You're dereferencing a null pointer. Well, that's just one way that it can go wrong, right? You could do a whole bunch of things that would go wrong. For example, let's come back over here to code spaces and refresh this. Sorry, while that's starting up. Ignore anything that might be there from the last session. Because we'll do it again. Come on. By the way, plenty of people are using alternatives like full VS Code installation. That can get quite complex because you need the VS Code, you need probably either GCC or Clang, which did it require MinGW? You didn't install MinGW?
No.
Okay. But then, no, I don't want to update right now. But it can get quite complex, especially if you're doing stuff that is given to you for free in the labs. So ignore all of this. There we go. All right. Int main. We'll just go ahead and go bare bones for now. Okay. So let me remind us how we actually create an array in C. Right. If I want an array of, say, size 10, right? You can do something like this, array of size 10. But remember that that's going to be static, right? Let me show you one consequence of that. Let's go ahead and create a function here called int or getOnes array. Right? So the idea here is that this function returns a new array of the given size filled with ones. There we go. Pretty simple, straightforward. Why you would want to do something like this, I don't know. But it does drive home the point that if you just create a regular old array like that, are there a bunch of ones in that array right now? Nope. It could just be random values for int I equals 0, I is less than. Let me go ahead and put that into a variable instead that we're going to take as input here. Right. I plus plus. There. Let's print it out. Printf. Array, so I %d is equal to %d and the line. And that's going to be I and then arrays of I. Let's find out what's in there. I'm going to say call main here, getOnes array. And let's just go 10. Right? Ooh, where am I? There we go. GCC demo. Yeah. We'll get back to that in a second here. Right. I just want to see what values are stored in that array. Well, does that all look like zeros to you? It certainly doesn't look like ones, but you get to random dead beef garbage, uninitialized memory. Okay? So let's change this from printing to actually initializing it. 1. Now let's return that array at the end of the function. Return array, so that down here I capture it. let's start up here. What is the return value here? Well, right now it's void. I'm not returning anything. Right? Should I return one integer? No, I want to return many integers. So in C, what does many integers look like? What does an array of integers look like? It's a pointer. Right? So down here, I will capture that pointer, int star array, and I will steal the code from up here to print it out. There we go. And I'm not going to set it. There we go. Good, good, good. I won't print it out up here anymore. Uh-oh. N is undeclared. Int n. There. Ignore that for a second. In fact, I'll shut it off. There. I'm not getting any warnings now. Just the hyphen small w shuts off all warnings. Okay? In fact, on code post, that's what we do. That's why we have two tests for everything. The compile test and then the warnings test. On the compiling test, we just want to know if it's syntactically correct. We shut off all the warnings. On the second one, we want to know if all the warnings are there. So we turn them all on. Then we go back and shut some of them off that don't matter. All right. So let's run it. Would you expect an array of a bunch of ones? That's what I would expect. Segmentation fault. Why? What happened? Later on, I'll show you a tool that will tell you what happened and where it happened, not the why it happened. That's you, right? Because again, you are responsible for it, right? Who's responsible for preventing forest fires? You are. Right? Who's responsible for making sure that segmentation faults don't happen? You. Right? So what's going on here? I'm calling a function, right? This is a static array. Do you remember where the static arrays are allocated? We've got function, calling function, calling function. These are stack frames. The array, in this case, is being created on this stack frame. When I return back to main, what happens to this stack frame? What happens to the top dish? It gets popped off and thrown away. Consequently, my attempts to access it down here are not going to work. This is why we need not static arrays, but dynamic arrays. Int star array is equal to new int of n. If it were Java, it would be that simple. Right? What's the equivalent of new? We need to allocate memory. We need to do memory allocation. We need to do malloc. Right? We talked about malloc on Monday, right? All right, good. The two things that I do are force it to become an integer pointer. Why? Because generally it is a generic void pointer. It's just giving you a chunk of memory, right? It can point to a bunch of integers. It can point to a bunch of doubles. We're going to say it's going to point to a bunch of integers, each of which is 4 bytes, 4 bytes, 4 bytes. Malloc takes one argument, the number of bytes that you want. Well, if I want n elements, and those elements are integers, how many bytes does an integer take? Size of int. There. Now, this will work perfectly fine. In fact, that's what the warning was about. It was saying you cannot return a static array from a function. But warning, it's not an error. Go ahead and do it if you want. You'll get a seg fault. I warned you about it. Right? But this will actually work. There. Now I've got a bunch of ones. So the takeaway here is you can return things from an array. I mean, malloc does that. Or you can return an array from a function. Malloc does it. Right? You can also pass values into a function. So let's do a sum function, a very simple sum function here that sums up the values in the given array. Dot, dot, dot. Well, if it's a sum, I'm going to return an integer sum. And if it's going to take an array, well, what is an array? How do we represent an array? As a pointer. I'm not going to create it, but I am going to iterate over it and sum them up. Int sum is equal to 0. Is that a good idea to name that sum? That's the name of my function, right? Sum plus equals. Right. So probably not. What should we rename this? Total? Total? There we go. Uh-oh. N is undeclared. Oh, that's right. All right. Is there a way that I can tell how big that array is before I get started here? Int n is equal to the size of the array. That is one of the most common mistakes. In fact, if you go onto Stack Overflow and ask a question, how do I tell the size of an array in C? You will get a bunch of answers that look something like this. They are all wrong, right? And it doesn't matter how wrong they are, they keep getting upvoted. I swear, I think it's probably like experienced C voters screwing with the noobs, right, that are doing that. And, but this is not correct, right? What this is, size of, array, that's a pointer. A pointer is 8 bytes. This will always probably give you 8. Right? There's not going to be 8 things in that array all the time. Oh, well, it's an integer array. So, int? No, that's 4 bytes. Right? That's not the number of elements in the array. They'll give you other garbage answers like, well, you could write a macro that does something, something, something. No. The truth is, there is 0 way for you to tell how big of an array is inside of a function. Instead, the function needs to be told. We need to pass, anytime that we pass an array to a function, we also need to pass the size of the array. This is the only way to do it in C. Don't listen to anybody else. Right? They are all wrong. So down here, once I get the ones array, I can sum it up. Int sum, or total, is equal to sum of array and n. And I can print out the total. Total is equal to %d. Stupidly, what would the total be here? I made an array of size 10 with all ones in it, so 10. But that's a good test case to make sure that it works. So the 2 takeaways here are when you're going to work with arrays and functions, right? You can return an array. It's got to be dynamic. You can give an array, but you've also got to tell it what's in there. You can also do, unfortunately, something like this. Oops, sorry, return total. There we go. I can do something like this. Array sub I is equal to 42. So what have I done? Now I'll go ahead and sum up your stuff, and then I'll immediately erase it with this magic number 42. Does that sound like a good thing or a bad thing? So let's create the ones array, print it out, the total, print it out again. I have ended up changing all your data. Good thing, bad thing? Probably a bad thing, because I just asked you to add that stuff up. I didn't say add that stuff up and destroy it. So here's the best practice. If it's going to be a read-only array, put a const in front of it. The compiler is now able to detect my attempts to change this on line 32 here and complain about it. In fact, it's no longer an error, a warning. It is now a full-blown error. Right? The assignment of a read-only location on line 32 is not valid because I made this a const. I made this a promise. I promise that whoever, I'm the sum function now. I promise whatever array you give me, I will not change it because I've got const in front of it. Right? Your data is safe with me. The compiler will catch me if I'm lying. Super secret, there are plenty of other ways to lie, right? In fact, there is a, what is it, underhanded C contest. All right, there we go. Underhanded C contest is a challenge that allows you to create valid C code that may not be caught by any compilers or anything like that, but that can do nefarious stuff, right? Like, look what I can get away with this language, right? There's also, yeah, there are a couple of contests like this, but there's a way that you can obfuscate. Oh, wow, that looks like really safe code. That looks like normal code, right? But no, because of ways, like my knowledge of C, I can do really, really cool stuff and screw with your data, right? That's just one way. Not that. There are ways of breaking that promise very easily so that you can think, well, my data is safe if I give it to this function. No, it ain't. Right? So there, I just mentioned that as a fun Friday thing, that if you want to go ahead and look at the underhandedsea.org, and they always have contests and such throughout the years. All right, I'll see you on Monday then.